There is a cloth making detail, which is really hard to make in 3D and especially to simulate. Because of its close proximity to other cloth pieces, the collision will be really hard to implement. It is called edge bias binding, and you can find it, for example, on the edges of backpack straps. So basically, it's a piece of fabric which is kind of sandwiching other parts. And in this video, we are going to make a fully procedural system to make this in a way which is fully stable in any animation pipeline, from deform modifier to cloth simulation. As for some of my previous videos, it is also part of my cloth making toolbox, which is still in the pre-release stage, but I am really close to finally releasing the first version of it. In any case, it's available to download on my Gumroad. So let's get to it. So first, let's create a base geometry to test everything. Here I just made a simple geometry that aims to emulate a backpack strap and with a few deform modifiers, so you can see how stable it will be. First I need to unwrap it so we have correct UVs, and now we can move on to the geometry node tab. Create a new group and let's call it edge to bias binding. Now before selecting edges and anything else, the first thing I want to do is to create a curve for the bias profile. Basically, we'll want a bias profile that can look about like this. So here we have our base mesh and instance the profile on the side. Now the easiest solution will be to first make a simple curve like this and then add bevels on the sides and eventually move some inner parts and the edges. And to do this, here we are going to generate a curve that will look a bit like this. Two curves on one side, duplicate them on the other side, and then we'll join everything with other curves. That way we'll have control over the fold position right here, in between the two curves we will create at the start, and by adding fillets on the sides, we'll be able to have this kind of shape really easily. So let's duplicate the group input, and we are going to add a few new parameters. Here I will want the bias thickness, which will be a distance with a minimum value of 0, and it will be a single value, and a default value of, let's say, 5 mm. Then you can duplicate these 2 times. The second one will be bias width, which can have a default value of 1.5 cm. And finally, we'll have a stitch placement input, which will just be a factor between 0 and 1 with a default value of 0.5. Now let's use these to create our curves. Add some curve lines. And for the start and end values, let's add some combined XYZ nodes. Just like this. Now for the start, we will just want a value on the x-axis, which will be the bias width multiplied by stitch placement. And for the end value, let's just put the bias width. Now let's create the second curve line. Here I will just want a combined XYZ on the end value. And for now, let's put the bias width multiplied by the stitch placement on the x-axis. Now we can join those two curves and take a look at the result. At the moment, the start and end values are the same, but I just want them to be slightly apart. So to do this really easily, we can slightly increase the stitch placement for the first curve by adding a multiply node by, let's say, 1.25. Now the curves are slightly apart, and we can change the placement with this value. Now let's clean this up a bit with some reroute nodes. At the moment we already have half of the curve. Let's translate it on the side by taking the bias thickness, dividing it by 2, putting this into the Y input of a combined XYZ node, and put this in the translation input. For the other side, I want to duplicate the join geometry node. This time the order of the inputs is really important, so for the first join geometry we put the two curves lines in the order in which we created them, but in the second one I will want the other order. So make sure the inputs are placed like this. And now we'll also put the transform geometry node with the same value, but scaled by -1 for the other side. Now we can also join those two together, and to make sure the orders will be perfect when we stitch everything together, let's also add a reverse curve node on the first two curves. And finally, to join everything together into a single curve, we can use the splines to curve node group I created in a previous tutorial, which will make everything look like this. So here you can properly see the importance of the reverse curve node, and here we should have a curve with all those control points. So now that we have our base curve, we can frame everything with Ctrl J and label this bias base profile. Now let's add some more control to tweak the bias shape. First we can add a fillet curve node. Make sure to set limit radius, and let's add a new group input node. Set the radius as a new input, which I am going to set as a single value and call it main fillet radius. I will set the fillet curve to poly and the count as a new input, which will also be a single value, and I will call it fillet's resolution. Now here I just want to set this first fillet on the two sides. But now, even if it doesn't look like this, we also filleted the 2 points that are on the middle of the curve. So to do this, the easiest way is to add a switch node, set to integer. I will put the count into the false value and the output into the count of the fillet curve. And for the switch value, I am going to select the endpoints value for the first 3 points and the last 3 points. That way, we'll have a value of 0 for the first and last 3 points, which are all the points here. And the last point will have the false value, which is the value we just inputted. And we can see the effect of this really clearly, because if I remove the switch node, the number of control points increases by the amount that will be filleted on the other 4 points. Now the second step will be to modify the shape of the endpoints and the stitch points. So let's add 2 set position nodes. For the first one, we're going to select only the endpoints. So add a new endpoint selection set to 1 on both the start and end. And for this shape modification, I want to add 2 new inputs set to vector, and those will be some kind of stretch values to stretch those points along a single axis, and the same for the end. So we'll call the first one stretch end. Let's put the default value to 1 for now, and duplicate this, and let's call it stretch fold. Now let's also put those as single values and reset the default value. And also, while we are at it, let's set the main fillet radius to a default value of, let's say, 2 mm. Now with the stretch ends, I will want to use the stretch value to multiply the position of the points. And now if I put this into the position input of the set position node, and you can right away plug this into the position input of the first set position node. Now if we tweak the value, we can already edit the shape of this part. Let's do the same for the second set position node, but here I will just want to select the points on the end, and the easiest way to do this is to select the 4 points on the end and just take all the opposite points. So let's duplicate the endpoint selection node, set the start and end value to 2, and invert this with a not boolean math operation. We can plug this as the selection right here, and for the position we can do the same, but selecting the stretch fold input we created earlier. And now if we tweak the values, we can have some finer control over the overall bias shape. And this works already pretty well, but now let's add the final step with a new fillet curve to smooth everything even more. Here the radius will be a new input value, which I am going to call stitch fillet radius, because I only want to reduce those 2 points where the stitch placement will be on the bias. This will also be a single value, and I will also put a default value of 1 mm. Here I am just reordering it near the other fillet value, and for the count I want to rename it fillet's resolution. And here the goal is to select just those 2 points and do the same kind of switch we did earlier. So I'm going to duplicate the switch node, put this into the count, and I will also put the fillet's resolution as the false value. And for the switch value, we are going to select the 2 endpoints and subtract as a boolean math operation a single point from the start and the end. And this will basically only select the 2 points where the fold is placed. And just to correct this here, because the selection is inverted, I want to put the fillet's resolution into the true input of the switch node. And now we have way better control over the overall shape of the bias. Here, if we want to remove this sharp angle here, we may also want to select the second point here, so we can set the endpoint selection to a value of 3 instead of 2, which will be way smoother. And all those nodes put together are allowing us to edit the shape of the bias binding profile really nicely. So let's join everything in a frame and label this bias curve shape. Now if all those fillets create overlapping points, we may want to remove them. So let's do this cleanup really quickly by setting curve to mesh, then merge by distance, and then mesh to curve again. And for the distance of the merge by distance node, let's arbitrarily put a value from our group input, which will be maybe stitch fillet radius divided by 4. So the visual aspect barely changes, but the number of points is greatly decreased. And finally, for the bias binding profile, let's give this some thickness. Let's add a set position node. Let's take our group input and add a new input value, which will be fabric thickness, a float value set to distance and single value, with a default value of maybe 0.5 millimeters. Now for the direction of the offset, we can take the curve tangent, which for now is only pointing into those directions all along the curve, and do a cross product with -d, so that we get some vectors that are all pointing inwards. Let's scale this by the fabric thickness and put this into the offset input. And here, if I set the value into the modifier, we should have everything slide inwards. Here we could have used directly the curve normal value, but it isn't always well defined on the endpoints, so the cross product method may work better. Now before the set position, we can add the capture attribute set to float and capture the spline parameter factor, so that we will have a value that goes from 0 to 1 all around the curve. And then we can reverse the curve direction after the set position node and join this resulting geometry with the geometry from the capture attribute. That way we have two curves, which will effectively give thickness to our edge bias profile. And finally, we can join those using the spline to curve node we used before, which was made in a previous tutorial. And after that, we can set it to set cyclic, so we have a fully enclosed curve. To finish off the shape, we can add the final fillet curve node, set to poly and limit radius, and here we can add those as new group inputs by duplicating the stitch fillet radius input and calling it detail fillet radius. And as this is a smaller fillet, we can arbitrarily set the count to the fillet resolution divided by 2, so we do not create too much geometry. Now this is really nicely looking, and to finish off this step we need a few more attributes that will be used later for shading. So first I will just capture at the end of this the spline parameter factor and put this into a reroute node with a label called factor, because this is just the general factor of the curve from 0 to 1 all around it. And I will also want a second one, which is just mirrored on the inside and outside of the curve. So to get this value, we are finally going to use the capture attribute we set before, and to get it across the spline to curve node, we can use a sample index node set to float endpoint, and here we can sample the geometry right before our splines to curve node and capture the resulting attribute right after it, so it isn't being messed up by the fillet curve node, which offsets the indexes of the points. The value we can plug it right here, and for the index, let's just get the index node, and we can finally put the capture attribute value from before into the value of this sample index node. Now if we take a look at this value, we should have a value going from 0 to 1 on both sides of the curve. So if you put it into a reroute node at the end of everything to find it more easily later, I can label this mirrored factor. And so at the end of the creation of the bias binding profile, we have a geometry and two different factor attributes that will be used for the shading a bit later. Now we can frame this final step with Ctrl J and label it bias thickness. So now that we have our base shape, so now that we have the profile for our bias binding, let's begin to process our geometry. First, to select what I want to process, I'm going to put two edge loops into a new group, which I will just call bias binding. So those are just the edges on which I want to instance my binding. Then, because for cloth making, we really often have to use a solidify modifier, I'm going to implement something to be able to work with it. So for this, I will just in a new vertex group called shell, and then if I add a solidify modifier before our geometry node, in the output vertex group, I just need to put the shell vertex group I just created into the shell input like this. This way, we will be able to sort the geometry in our geometry node system, because without it, we will have duplicated the geometry on which we want to instance our edge bias. So now, let's go back into our geometry node near the default group input. So here we are first going to select the geometry. I'm going to add a first separate geometry node, and for the input, which I'm going to rename solidify shell with the default attribute called shell. Now into my modifier tab, I can switch this to attribute and select the attribute shell I just created and which gets its data from the solidify modifier. So from this, instead of getting the full geometry, I'm just getting the base geometry before the modifier on the inverted output. So this is where we are going to get our geometry. Right after that, I want to separate my geometry 2 more times. So the first 2 times we are selecting and the final time we'll only get the selection itself. For the final step, we are going to use the same trick as in another video of this asset pack, which is to use an accumulate field to accumulate the value of the selection on which we want to put our edge bias over the island index, which will allow us to only select the mesh islands on which at least one of the vertices has a value different from 0 for our selection. So for this, I'm going to put the value as a new input, which will be the edge selection, and in the modifier tab, I can right away select my bias binding vertex group. And here we can put a default value of 0, just to make sure that it doesn't instance edge bias everywhere on our mesh when we put the modifier on a new geometry. And then I can put the total output in the selection of the third separate geometry. Now for the second one, I can put a named attribute node, and here we didn't set this up for now, but I just want to make sure I am not selecting any kind of geometry I created before with any of this modifier from my asset pack. So this attribute will also make sure to prevent to instance some edge bias onto some other edge bias we created before. And here the name of my attribute is just cmtb_generated for cloth making toolbox generated geometry. And this is also an attribute that we will set up manually right before the final group output of this setup. So this is the first sorting of geometry, which will allow everything else to work way faster. We can join everything into a frame and rename this select geometry. Now to start processing everything, we can right away add another separate geometry just to turn everything into curve. And here I want to select my group input, and the edge selection, I'm just going to check if it is equal to a value of 1. So this will also make sure that it works with subdivision surface modifier even before this geometry node setup, because it can have the effect of blurring our edge group selection, and this result I can put into the selection of our separate geometry. And right after that I can convert this to curve. Now before this I want to capture a few attributes which will be useful later. So I will first set two capture attributes set to vector. The first one will capture the base normal value of each point. Then we'll also need the position, because we will do a bunch of computing into the UV space, and we want this value to go back to the original position space. And speaking of it, we are just going to move everything. We are just going to move everything to the UV space with the set position node, on which I am going to set the position as the new input. And here I'm just going to rename it UV map with the default attribute of UV map, which is the default name of the Blender UV map. And I can also select it onto our modifier tab right here. And now that our curve is in UV space, I just need to capture again the normal value. So we have both the normal value of our mesh in the original space and the UV space, because we did everything before we turned our mesh into curve. Now let's just clean this up a bit and frame those new operations with Ctrl J, and this is curve pre-process. So now with our curve in UV space, we have one more problem to fix before moving on with everything, and that is that the direction of our curve may be inconsistent because of the way Blender converts a mesh to a curve. So right here I have my curves here and here, and ideally if the mesh is on the inside, we want the direction of one curve to go in one direction and the other in the other direction, so that we have a consistent outwards direction, but it may not be the case. And to correct this, I have a small setup that we already discussed in a previous tutorial, so I'm just going to make it really quickly, but I will link to a more detailed version of this in the description. So here I'm capturing the attribute of the index of each spline, sampling the curve by factor at the midpoint of 0.5 with the curve index we captured just before. Here I am doing the cross product of the tangent and the UV space normal we captured just before, scaling this by some value, which will be a new input, which I will set as a single value called curve reverse threshold with a default value of 0.001 and a minimum value of 0 and maximum value of, let's say, 10. This I will add to the position and sample the UV surface of our source geometry before we moved into UV space with the value set to vector and the value and sample UV set to the value we just added before, and the UV map will be the UV map from our group input. And finally, I'm going to evaluate on domain the isValid output with the domain set to spline, reversing this value, and put this as the boolean input of a reverse curve node, which is going to reverse the curve we have after our capture attribute right here. And this I can output to my group output. And let's just remove the viewer node. So now I'm just going to put everything into a group, Ctrl J, and rename everything. Geometry is curves, the UV map is the source UV map, the other vector is UV space normal, the scale is the curve reverse threshold, and the mesh is our source geometry. I'm just reordering this. And this group is a fixed curve direction block. Now this is way cleaner. Just putting a reroute node right here. And after this, the next step is to go back to the original coordinate, so move out of the UV space. So for this I'm going to set the position with the capture attribute position from before. And I'm going to set this as the group output. So basically here, moving in and out of UV space just allowed us to have consistent curve direction, which will be essential for the other operations. And the last thing we need into UV space, so before we move back out of this with this set position we just added, is I need to capture the length of the curve, and this is also better to do into UV space. so it will stay consistent with any kind of deform modifier, simulation, or anything else. So this will be a float value, which I am going to call cloth making toolbox underscore curve underscore length. And for the value, I want the length of the spline length node. So at this stage, our curve all have consistent direction, but they may not have consistent tilt. And here we basically want to have a consistent normal direction onto our curve, so that the direction of the instance object will be consistent with the normal of our base mesh. So let's join this block, and let's name this step correct curve parameters. Oh, and also let's rename this group align curve normal, and set the tilt value into the modifier to its default value. Just a quick word from editing me, I found a better way to fix the curve normal direction, which is a new input on the set curve normal node, which we can set to 3 and manually choose the normal for each point. So for this we can still select our captured normal from before moving into the UV space, which is right here for me, and then we can use a vector rotate node set to axis angle, with the axis being the curve tangent and the angle or tilt angle parameter, to which we are going to add pi over 2. So here the tilt parameter I added in the previous method is just a float value set to angle and a default value set to 0. Now let's allow to offset the curve so we get a bit more control. Let's add a set position node, and here let's first take again our captured normal value from before, which we can scale and put into the offset. Let's put this to 0 for now. Then we are going to add another scaled value, which is going to take the tangent value of the curve tangent, and a third control, which is going to take the input of our captured normal, and let's add a third control, which will be a scaled version of the normal of the curve we just fixed before. So now to control the 3 values with a single input in the geometry node tab, let's add a separate XYZ node, put the X, Y, and Z value in the 3 scale node we just added, and let's add the vector, add a new input in our group input, which I'm going to set as a single value called bias offset. Let's clean this up a bit, frame this and rename curve position, and finally I like to allow to set the spline type to NURBS for added resolution. So for this I'm just going to set spline type node, set to NURBS, and for the input a new geometry node input, which is going to be a single value called set NURBS, with the default value set to false. And also while we are at it, let's set the bias offset to a subtype translation, so we have values in meters. So now let's add a step to change the length of the curve with a trim operation. So let's add trim curve node. And here we could make it consistent with deformation by using the factor, but I want to use the length parameter so that we give simple input to the user. So for this, we can take the actual spline length, divide this by our attribute for the curve length we created before, so cmtb underscore curve underscore length, so that we get a kind of factor. And now we can multiply this by a user input, which will be the start value in meter. So we can get this new value in the settings tab, rename it trim start, set this to subtype distance and a default value of 0. And we can also set it to a single value. Now we can duplicate this parameter for the trim end, which we can also multiply by our divided factor. And because the end value is referring to the maximum distance of the curve, we need to take our spline length and subtract this new value. This way, we get trim parameters for the start and end, which are really precise. And this is just the trim curve step. Next, let's resample this with a resample curve node, set to count. And here, let's take a group input. We can also duplicate the parameter for the trim end so that we get a single value expressed in meters, and rename it resample step size. So now if I plug it into the selection, we first get no resampling if the resample step size is set to 0, and then to compute the value, we can take again our named attribute which stored the curve length and divide it by the step size so that we get an integer value which will be the new point count. And this again will be more consistent than to use the length parameter, which may give inconsistent results with deformed animations. Again, let's join this, and this is resample curve step. And now we finally get to the end part, which is to create the edge bias, and finally we will compute some output attributes, and this node will be ready. So with this resampled curve, we can add a curve to mesh node, and the profile curve will be the bias profile curve we created earlier. Now let's output this. Right away you can see that the result is pretty consistent. So in the end we can right away join this geometry with the source geometry from the group input. Now let's just tweak a bit the parameters so that it can work better with the solidify modifier I added earlier. So I'm going to offset everything a bit. And this way it's looking really nice. Now let's also add a new input parameter for the fill cap input so that we can decide to add this or not. Now let's take a few output attributes. Here I need to capture an attribute which will correspond to the distance of the points from the start of the curve. So for this we could just use the length attribute from the spline parameter input, but again it will be inconsistent. So here we can take the factor input and multiply this by our named attribute, which stored the fixed curve length from the UV space, like this. Then after we convert this to a mesh, we can capture attribute again, this time a vector, and here we can plug a combined XYZ node. Now let's plug this new length parameter as the X input, and now the Y input can be the mirrored factor, and the Z1 could be the factor from the bias thickness block we created earlier. Now we can right away output this as an attribute, which I am going to rename UV bias, and with the default attribute name called UV bias. Now we can add the usual final steps, which are set shade smooth, set material, which we can add as a new input, and then we need two final attributes before we can move on to the shading tab. One is the one I talked about earlier, which is to store a named attribute, which will be a boolean value called cmtb underscore generated, so that we can know which geometry comes from the base mesh or from my cloth making toolbox. And then we can also add a capture attribute, which will act the same, but will allow us to differentiate which bias may be created by which node group. So this we can just set to true on this branch and output this as a group output, which I am going to call new geometry. And here I am going to set the default attribute to bias underscore binding, and I can paste this right here. And with this final step, our work in the geometry node tab is complete, so I can join this into a new group and call this output attributes. And so this whole thing is pretty clean. So now let's move on to the shading tab to see how we can work with this. But first, as you can see, the whole behavior is really consistent with any kind of deformation, however extreme it may be. And this is all thanks to the step we did in UV space. So now in the shading tab, let's create a first material for the cloth itself, and a second one for the bias binding, which you can allocate to the new geometry in the modifier tab of our geometry node. So just to make sure it's working, perfect. So now we can take our attribute called UV bias, which stores the whole kind of custom UV map we created, and let's separate its coordinates so we can work with it better. So now, if you remember correctly, the X value stores the length of the bias, the Y value stores a value which is going all around the bias but mirrored on the inside and outside, and the Z value stores a value which is going all around the bias. So if you want to map a texture, for example this texture from Polyhaven, I can map X and the value to create a new UV map, and then with the mapping node I can compress everything on the X-axis, which gives a really nice mapping of this texture, and most of all it is absolutely stable with any kind of deformation. Now another example is what we can do with the Y input. So this is the mirrored value. If I subtract 0.5 and take the absolute value, I have a new mapping of this mirrored value, and if I do this one more time, I can get a value which I will be able to use to drive a bump node. So now if I multiply this, so I can scale this, make sure to clamp it, so I can set the width of this bump, and with the float curve node, I can, for example, set a bump profile like this, which I can plug into the height input of a bump node, which, with a lower distance, can give a really nice added depth, and I can control the width of it with this multiply value, and the position with this subtract. So like this, I can add a bunch more detail with this low poly geometry, and you can do way more things by combining all those different attributes we created in the geometry node setup. Now, one more really cool thing is that for the moment we are mainly missing the stitches, and if I don't want to create them with textures, I can also use my Topstitch node group, which I made in a previous tutorial, and for which the new version will be coming out really soon, but I can already showcase here. So here I added the group 2 stitches setup and the stitch curve 2 mesh, which will allow me to add stitches to this really easily. So right now I have way too much stitches, so I can increment the stitch step size, reduce its width, change some offset parameters, so it is placed at the middle of my geometry. Perfect. Now I can give it some thickness by setting the right attributes, and now this whole system is working really nicely, even with lots of deformation. And for a quick preview of this upcoming setup, here with my new stitch setup, I can change the type of stitches, which also allows for way more detailed stitches with multiple threads and much more. Now I am going to create a really nice demo piece for the thumbnail of this video and the asset pack itself. I hope you liked this video. Don't forget to like and subscribe if you are into that. Thank you for watching and see you next time.